All right, in this video, we're going to take a look at some more examples identifying conic sections that are in polar form. So example 3a, we're going to identify the conic section for r equals 4 over 1 minus sine theta. So notice in this particular example that the value of e is 1. So if e is 1, that's going to indicate we have a parabola. So if we take a look at the graph of 4 over 1 minus sine of theta, we have a parabola where it's opening upward and our vertex is at 0, -2, and our x-intercepts are at plus or minus 4, 0. So it's a parabola. Since e is equal to 1, it's going to open upward. Vertex, as we said, is 0, -2, and our x-intercepts are at plus or minus 4 and 0. In part B, we have 12 over 3 minus cosine of theta. Well, in this one, notice the 3 that we have down below. In the last example, we had 1 minus, and in our other examples, we also had 1 minus. So if we divide everything by 3, we get 4 over 1 minus 1/3 cosine theta. So notice this time that e equals 1/3. So we can graph this. We can also graph the original conic section as well. So here's the original, which would also be 4 over 1 minus 1/3 cosine theta. Notice we do have actually, it looks very close to a circle, but it is actually an ellipse. So if e was equal to 0, then we would have a circle, but e is between 0 and 1, which is going to mean that we have an ellipse. And in this case, because it's cosine, it's going to be a wide ellipse versus a tall ellipse. So with e equals 1/3, which is between 0 and 1, we have a wide ellipse. And, well, you have an ellipse, but again, it's wide because of cosine. Very close to 0. 1/3's really close to 0. But if it was 0, then we would have an actual circle. So we have e is equal to 1/3, and 1/3 times d is going to give us 4, which makes d equal to 12. So d is going to equal 12, which means that our major axis length is going to be 2 times e times d over 1 minus e squared, which gives us 9. And if we take a look at our graph here, because it is wide, we have from one vertex to the other a distance of 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have one vertex at -3, 0, another at 6, 0. Our minor axis length is going to be 2 times, it's essentially the same thing, but taking the square root of the denominator, which in this case, after we rationalize everything, will give us 6 times the square root of 3. So our minor axis length, which is going to be this height of our ellipse from the center, is going to be 6 times the square root of 3 after we rationalize our denominator. So I encourage you to get this calculation of 6 squared root of 3 by simplifying this and rationalizing the denominator. All right, example 3c, r equals 6 over 1 plus 2 sine theta. This will be our last example in this slide, or in this video. So let's see what that graph looks like. Before we do, actually, let's see. We have e this time is 2, so e is bigger than 1. And as we said in the previous video, that when e is bigger than 1, we got ourselves a hyperbola. And it's opening up and down because of the sine theta that we have. If it was cosine theta, then we would have opening left and right. So we have a hyperbola. The transverse axis is, or the traverse axis rather, is the distance between the vertices of the branches. So we do have a hyperbola opening up and down. 2 times d is, e is 2, so 2 times d is going to equal 6, means d is 3. So our traverse axis length is 2 times 2 times 3 over 2 squared minus 1, which is 4. And again, we can see that in our graph. We go down 1, 2, 3, 4. So this distance is 4. Our conjugate axis length is going to go left and right, and it's the same process, but instead of the denominator of 3, it's the square root of 3, and just rationalize 12 over the square root of 3 simplifies to 4 times the square root of 3 for our conjugate axis length. All right, that about does it for this video, and